Okay, we're moving on in chapter 6, and today, really two objectives. We're going to be solving exponential equations, and then at the end of the class, we're going to solve exponential inequalities. Sandwiched in between those, we're going to take a look at a particular type of exponential growth function, probably the most popular real-life exponential growth situation, and that is compound interest. So we're going to look at some application problems that involve compound interest formula and how to use it. So first of all, if you don't have a calculator, we need to make sure you get one. So let's go ahead and take care of that now. Okay, so let's get right into some examples. In these problems that I've marked for you, problems 9 through 14, the instructions are to solve these exponential equations. And this is going to involve a technique that's really going to come in handy for you in future, maybe college algebra classes where calculators are not allowed. This is going to be great that you understand how to do this technique called the common base technique or process. And after we've done a few, you'll understand why we're calling these, or this, the common base process or technique. Here's the goal, here's the objective behind solving for x, which is, as you can tell, x is involved in these exponents. To solve for x, I'm going to rewrite this equation, and the goal is to rewrite it so that I'm using the same base to represent each of these numbers below the exponent. Let me give you an idea. Let me give you a sample of what I'm talking about here. I already know by looking at this problem that I could rewrite 27 as 3 to the third power, right? So I'm going to turn this into an equivalent equation, but instead of writing 27 on the right side, I'm going to show it as 3 cubed. Still 27, but written differently, but equivalent. And I'm just going to bring this exponent down. It already exists. So think of 3 cubed replacing just the 27 in this equation, and the 2x minus 4 just gets brought down as being part of the equation. Well, here's the great thing about the common base technique. Here's why we call it common base. I have, base means the number below the exponent, and I've got that same number written as a base on either side of the equation. When you get to this point, solving for x is really pretty easy because I just let the exponents equal each other. I'm going to make an equation out of the exponents. So I'm going to say 5x is equal to 3 times 2x minus 4. And we're doing Algebra 1 stuff now. Don't forget the distributive property. 5x equals 6x minus 12. Negative x is negative 12, so positive x is positive 12, and that is my solution. So the great thing about this is, once you get to common bases, that's what this equation represents, you're essentially solving the exponents. You're letting the left exponent equal the right, and you solve it. But you can't do that until you get to this common base line. And that's going to be your goal, finding that number that represents the common base. All right, let's try another one. I'm observing the two bases. I've got 16 as a base on the left side, and I've got 4 as a base on the right side. Well, it probably is obvious to you that I could write 16 as 4 squared. So I'm going to just rewrite the exponent that was given in the problem. And this right side base is already 4, so I have common bases. That's the goal. And once I get to this part, I just let the two exponents equal each other to solve for y. And let's just go ahead and do the distributive property. This would be 4y minus 6 equals y plus 1. subtract y from both sides, add 6 to both sides, divide by 3, and our solution for y is 7/3. Any questions so far? None? Okay, very good. Let's try this one. Oh, yeah. Question? Okay. All right. Let's try this one. Any volunteers? John. So you're going to rewrite 32 as 2 to the 5th. That's good. And there's already an x minus 2 there. And we will eventually multiply these together. We don't have to do anything to the left side. It's already got a base of 2. And now that I've got common bases, Kennedy, tell me how I will solve for x. Okay, very good. Okay, 5x. And our solution for x is negative 10. Very good. All right, let's try another one. Let's see, Jalen, can you help me out? Seven squared. Okay, I'll go ahead and just finish writing. So you went ahead and multiplied these together. 2x plus 10. Very good. Very good. You could. We use the expression kill the little one. I'm going to subtract 2x from both sides. What you said is not wrong, but that keeps us away from having negatives to divide by. Add 6. Okay. And what's my final answer for x in reduced form? Reduced fraction form. Try it again. I think you just need to flip it over. Not 3 over 8, but 8 over 3. Yeah. Any questions? Not bad, is it? Okay. Roman numeral 2 is another type of problem. You're going to do 5 of these. One of them's a word problem, and then you got 4 that basically look just like what I've done here on this slide. If you think about it, it's kind of the reverse of what we've been doing the past couple of days. Past couple of days, it's like, here's an exponential growth or decay function, give me the ordered pairs and graph. Well, this says, here are the ordered pairs, give me the function. So we're going to work in the reverse direction. Well, I gave you a great place to start on your notes. This is the template, if you will, for exponential growth or decay. So what we're going to do is take the information that we're given, and we're going to be able to plug in for just about every one of these variables. Actually, every one except for one variable we can replace. All right? So going back to what we've just covered, the y-intercept, which you will be given, here's the y-intercept. Notice x is 0. The y-intercept is 6.4. Well, maybe you remember this. The y-intercept will always be which of these variables in this function? Okay, let me phrase it this way. The y-intercept you could also think of as the beginning number or the initial number. We're starting from there and then we're either growing or decaying. Yep. Very good. So the y-intercept that will always replace the a in this function. So for now, I'm just going to label. Well, let's see. We've got to replace x and y. Any thoughts on how we can do that with what we're given? Yes? I need numbers to plug in for x and y. Do I have them? Mm-hmm. Yeah, what about these? What's 3 represent in the ordered pair? 100? Y. Okay. They just handed me numbers to plug in for x and y. So what's the one variable I don't know yet? B. So we're going to solve for B. So let's plug in everything we know. 100 equals the y-intercept, 6.4. We don't know B yet, but we're going to figure it out. And x is to the 3rd power. So let me get Chris. I'm trying to solve for B. I've got a couple of things that I have to undo. I've got to undo multiplication, and then I've got to undo this exponent 3. But if I go in reverse PEMDAS order, which of these would I undo first? Multiplication or the cube? I'll give you a visual. Here's PEMDAS, and we're going in reverse order. So which would come first in reverse order, multiplication or exponent? Okay, so I need to undo multiplication first, and what's the opposite of multiplication? Division. All right, so what am I dividing by, Chris? Okay, so let's do that, and you'll probably want your calculator for this. 100 divided by 6.4. Sam, can you give that to us? Give me the decimal. Okay. And let me give you a little tip if you didn't already know this. This will keep you from having to retype stuff in your calculator. I now need to, well, you tell me before we go to our calculator, describe for me how I'm going to find B. Yes? The cube root. Here is a good way to do any root that you want to without having to go into another area in your calculator and retype this number. Is 15.65 still on your screen? Okay. Then just hit this caret button. You see that? The upside down V? And in parentheses are very important, you can raise that to the 1/3 power. Raising something to the 1/3 is the same thing as doing the cube root. $2.5. We found B. So raise your hand if you got 2.5. Great. All right, we got all the pieces. Now we're ready to put all the pieces together for our final answer. We're supposed to write a function. So y is equal to a, which is again the y-intercept, times b, which we found as 2.5, raised to the x power. So this represents the final answer. So make sure when you find all the pieces that you put the pieces together as a function. And that's the only example I have of these, but if you have questions about that, I'll be glad to take them. I think if you start here, like I've shown you, and you know what to plug in for everything but B, you should be able to come up with your answer. Question? All right, part 3. You guys are doing great. Hang in there. Compound interest. Somebody give me your own definition of interest in a good sense. I know there's an interest in a bad sense, referring to debt. Lindsay, give me what interest is from a good investment sense. Okay, good. How many of you have your own savings account in a bank? All right. Unfortunately, today, banks pay very, very, very little on just regular savings. I don't know if you ever noticed. Do y'all pay attention to your account? Yeah, it's real small. You might get a penny or two here and there, depending on how much money you have in your account, but it's just pennies interest that you're earning. But there was a time back in the 90s where it wasn't uncommon to have savings accounts, just general, regular savings accounts like you guys have. They'd pay 5-6%, which you might think, well, what's the big deal about that? Well, it's better than a few pennies. You get a few dollars. But interest is the bank's way of paying you money. What do you think they're going to do with your money when you give it to them?
They're going to loan it out to other people.
They're going to invest it, or they're going to loan it. They're going to make interest off of your money. And then they're going to turn around and give you a few pennies for the opportunity of investing your money. Okay? They're going to make a lot overall. They're going to give you a little bit for the opportunity to hold your money, and they're going to, like you said, they're going to invest it. Well, let's add the word compound. We know what interest is, but what do we mean by compound interest? That is interest that earns interest. Okay? So those few pennies, let's say you put in $100 into your account, and after 1 month you earn 2 cents. All right? Well, now you get your bank statement or whatever it is. Maybe you're looking online, and after 1 month you have this. Whew, I got 2 cents. Well, compound interest says that next time when interest is figured, it's going to be based on this. So I'm going to get interest on that little bit of interest that I've already earned. Okay? So that's why, if you think about it, it's a perfect example of exponential growth. So we have this formula that we're going to use, and you're going to need to know. I'm going to ask you to be able to use this on your test. This is the formula for compound interest, but we need to make sure you understand what each of these letters represent. So I'm going to walk through that with you. So the A in our formula, this capital A on the left side of the equation, you can think of that as the amount earned after interest is applied. So for example, I put in $100, maybe I get $20 worth of interest. A would be $120. It's my original investment plus the interest that I earned. P stands for the initial investment. In my previous example, that would be the $100 that I put in the bank. And you might be wondering, well, why do we call it P? Well, the P stands for principal. So if you ever take finance classes in the future, P will stand for principal, which is just another way of saying, what did I invest? First day. What did I take to the bank and let them keep for me? The initial investment. R stands for the interest rate. But this is so crucial. I hope you listen carefully, because some people don't and they end up missing these problems, and this is a common mistake in using this formula. You always, always, always need to take the given interest rate, which will be a percentage, and you need to change it to decimal form. Make sure you change percent to decimal, or else you're going to miss the problem. We're going to talk a lot about N on the next slide. I'll put a little star by it. For right now, let's just identify N as the number of, we'll call these compounding periods. In a year. In other words, how many times during the year will compounding actually take place? N will tell us that. And T stands for how many years, the number of years we invested our money. T is always years. Okay, so before we actually apply this formula, let's do something that some people struggle with. Let's identify some common compounding periods. What is the numerical equivalent that we'll plug into our formula for each of these words? Well, monthly means, you probably guessed, 12. N would be 12. 12 times a year, if compounding is monthly, then we're going to get our money compounded 12 times in a year. What about quarterly? N would be 4. Bi-monthly. That means, bi means think of every other month. 6. If the problem told us that interest was compounded bi-monthly, we would plug 6 in for N. Weekly? 52. 52 weeks in a year. Semi-annually? 2. Just think of once in the first 6 months and then once in the last 6 months. Annually, of course, would be 1. So get familiar. It depends on the problem. You need to read carefully what the compounding period is, and then you can plug in the appropriate number. So now let's apply it to this particular problem. And you're going to do 4 of these. They're all basically just like this. We have this investment of $2,500. It's paying 4.2%. Annual interest compounded monthly. So what's N going to be? 12. All right, and we want to know what this original $2,500 is going to grow to become after 15 years of compounding interest at this rate. So I'm going to give you this so that you can just put all of this in your calculator at once. There's no reason to break this up into parts and key in multiple things. Let's just do it all in one line. So here's our formula. The final amount, that's A. We will take our initial investment of $2,500. And if you're keying into your calculator, you can just do $2,500. Left parentheses. 1 plus. The numerator is the rate, but don't forget, we got to change this to decimal. 4.2% is 0.042. Just slide the decimal 2 places to the left. Below the rate will be the number of compounding periods. You've already told me that is 12. Right parentheses. Now, if you're using your calculator, this is how we raise to an exponent. And the exponent needs to be in parentheses because we're going to let the calculator do this multiplication for us. I'm going to go back to the formula and then I'll come back. This means N times T. Whatever N was, we'll multiply by the number of years. Well, here's another common mistake. Letting the calculator do that but not putting it in parentheses. That'll really throw your answer off. So parentheses, N is 12. Times, and the number of years, that's T, 15, close your parentheses. So all of that entered in at once will get you your answer, and I've given you a note here in blue. Anytime you're asked to do an interest problem, we're going to round to the nearest penny, 2 decimal places. So I'll give you a few seconds, and just want to make sure that everybody is able to get this answer. $4,688.87. Okay, I think just about everybody got it. I saw a rounding thing. So to the nearest penny means 2 decimal places. And anytime, I'll just go ahead and make a blanket statement. Anytime you're doing these interest problems, that's the way you'll round. So if I forget to tell you on the test, you'll know what to do. Any questions? Okay, any questions before I leave this? You've got, 4 of those? Read carefully about what the compounding period is and what the rate is, but they all work pretty much the same. All right, these problems, they're going to look a lot like what we did with solving exponential equations. We still are going to use that common base technique, But now our answer is going to be a range of numbers instead of just one single number. These are inequalities. And these are a little trickier, I guess, in finding the common base than what we looked at previously, because in the previous examples you could see the common base on one side. You know, you could pretty much tell what it was going to be because you'd have 3 over here and 27 over here. You knew the base had to be 3. Well, here I can't exactly see the common base. Please don't say the common base has to be 8 because 8 squared is 16. I get that a lot. 8 squared is not 16. So, any thoughts? Raise your hand if you got a thought about what the common base needs to be. Lindsay? Well, not exactly. We're thinking about a number. We could do 4 to the second to get 16, but we can't raise 4 to anything to get 8. So it's got to be the same base. Jalen? Good. 2 to the 4th is the same thing as 16. And over here we can do 2 to the 3rd. And now, once we, just like we did before, we're just going to let the exponents equal each other. 8x minus 12 is equal to 3. 8x is 15. X is 15/8. Okay, questions? Oh, man. Sorry about this. Somebody should have stopped me. This is not an equation. Yeah, it should be less than 15/8. Sorry about that. Got carried away. Please don't do what I did. Make sure if it's an inequality, you write your answer as an inequality. All right, let's try another one. Sam, give me the common base first of all. Good choice. He said 3 is going to be the common base. The question is, Sam, 3 to the what power is going to equal 1 over 243? I'll give Sam a shot at this and then turn it over to somebody. -5. 3 to the 5th is 243, but if we want the reciprocal of 243, then that takes a negative exponent. Yes? So the great thing is now that we're in common bases, we just let the exponents equally, or not equal each other. We set them up as an inequality. 2x is greater than or equal to -4. So all the numbers greater than or equal to -2 should make this true. Questions? Think you got it? You're catching on really quickly. Let's try this one. I'll go back up to Kennedy. What do you think the common base is going to be, Kennedy? Good choice. So nothing to change on the left side, but we got to think about how we can -5. Very good. 2 to the 5th is 32. So the negative makes it the reciprocal of 32. Let the exponents go together in the inequality. Just pull out the exponents and, yep, all the numbers greater than -7 will satisfy this inequality that you're given. Well, let me start with this. 2 to the 5th is 30. We know the base has to be 2. 2 to the 5th is 32. But to make it the reciprocal of that, then you just change the exponent to negative. Any questions? Okay, this is your assignment. I don't think I gave you that slide. But this is what we'll check Friday.